Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. I hope you are enjoying the study of many degrees of freedom interacting with each other and producing phases. So we have completed 7 chapters in the course so far. Today we'll start a new chapter. So before we start the new chapter, it's a good idea to have a discussion of what we have done in the course. So this is the summary, and please ignore this TFIM. So many interacting degrees of freedom, when they have interactions between them, they will produce phases, and these have continuous phase transitions that have universal properties. To study the essential physics of such problems, we make up models, and many times these models are informed by symmetries. So we have seen that to characterize phases, particularly where symmetry is broken, we have the notion of an order parameter, and this order parameter becomes a very interesting quantity to study, both from the experimental and theoretical points of view. So we have studied many interacting models now. For example, when we studied the interacting particles model, we performed analytical calculations based on a small parameter, which was the fugacity. And it's not often that one can get away with such expansions, but they are very useful in understanding at least some limits of the theory. We then moved to study the classical Ising model, and what we learned from the classical study of the classical Ising model is that there is a very strong dependence of spatial dimension in determining phases of many particle systems. So for example, 1D Ising model does not have a finite temperature phase transition, whereas 2D Ising model does. We learnt about the key idea of duality, which allows us to connect apparently different problems. And then we moved on to quantum models, where we saw a rather interesting and very useful result, which is that quantum models in d dimensions in equilibrium are equivalent to classical models in d+1 dimensions, with possibly different coupling constants, of course, but there is a connection between these kind of systems in different dimensions. So we exploited that to study the properties of the two-dimensional Ising, classical Ising model, by studying the ground state of the transverse field Ising model in one dimension. And one of the central outcomes that came out of that discussion of the transverse field Ising model, which mind you is an exact solution of the problem, is that at the critical point, for example, or in and around in the vicinity of the critical point, you can have new emergent symmetries at low energies, at long wavelengths, at long length scales. You can have symmetries that are emergent. So you started off with a system with a certain set of symmetries, but because of the interactions between the degrees of freedom and so on, it organizes itself into a state which seems to have extra symmetries that you didn't put in. Okay. Another very important observation is that the critical point that we discovered in the study of the transverse field Ising model did not have any intrinsic scale in it, and we call this state scale invariant. We will have a lot more to say about scale invariance later in the course. So the motivation for starting the next chapter today is that it's not often that you can pull off an exact solution in statistical mechanics. In fact, exact solutions are rare, one would say. Okay, so we need to come up with approximation methods, and you see that we have this phrase here, non-perturbative, and we will discuss what is non-perturbative approximation methods and how they somewhat differ from these sort of expansion techniques and so on. Okay, so let's try to understand why we are interested in these non-perturbative approximation methods. Okay, so we solve the quantum Ising model or the transverse field Ising model in one dimension, we were able to solve this exactly, and we know that the physics of that describes the two-dimensional classical Ising model and its phase transition at finite temperatures. Suppose I ask the same question, can I do this in 3 dimensions? Then the community has been working on this quite a bit, but at least as of the taping of this lecture, I am not aware of an exact solution of the 3-dimensional Ising model. So, what is the problem? The problem is the regime where we want to study the model is in the non-perturbative regime, right? So, typically the way we studied the problems when we did the series expansions, etc., is we found a small parameter and we perturbed about a known state. But if you look at the classical Ising model in 2 dimension, which we solved, essentially found the TC exactly by duality, we know that the TC is something like twice J. So, the dimensionless coupling constant, for example, in 1D Ising model, transverse field Ising model, the 2 scales, the dimensionless parameter is 1, which is certainly not a small number. And in particular, you will see that some coupling constant in 2 dimensions is something like of order 2. So, these are not small parameters, or we cannot perform reliable expansions by simply pretending that they are small parameters. You can do it, but it may not give us reliable results. And if we go to 3 dimension, for example, the problem gets much more difficult, as I mentioned, and there is no obvious small parameter, particularly in the regime of interest, namely the regime around the point where phase transition takes place, etc. So, what we would like to do is we would also like to have some very quick and dirty ways of finding out the phase diagram of a given model. And the reason for that is, it's oftentimes we will see some phenomena, we will make a model that we believe can describe that phenomena, so that we can study such a model, we can make some inferences, and we can tell our experimental friends to go and check something or the other, or to do a new set of experiments. For this, we need to know whether the model that we have has at least essential contents of the physics that we are looking for. So, from that perspective also, we would like to develop techniques that are easy to implement, that are easy to work out, and so on, and so that we can get an overall idea of what is the physics content of our model, if not all the details. Okay. So, this is the idea of trying to develop non-perturbative approximate methods. And what is the strategy for developing non-perturbative approximate methods? Okay. So, there can be many different ways of doing this. So, you can broadly categorize these as what we call as variational approaches, or you could use some physics based approximations, which is you take the Hamiltonian and you make certain approximations in the Hamiltonian directly. And what we will do is, we will see examples of both of these approaches in this chapter. So, before I describe some of these methods, I want to emphasize that much of what we will do in the remainder of the course will be based on classical equilibrium systems. It will apparently appear as classical, but as you can appreciate, this could also describe the ground states of some quantum systems in one lower dimension. So, we just focus on classical systems and work with them, and if we need to work with a quantum model, many of the ideas that we will be developing can be fairly straightforwardly generalized to quantum system as well. Okay, so let me state the problem a little bit more carefully. Suppose I have some arena on which I have degrees of freedom defined and so on, as we have done in the past, and let us say see some configuration of these degrees of freedom. So, there is some Hamiltonian that describes the energy of this configuration. So, that is what we call H of C. So what I want to do is I want to evaluate the partition function, and the reason why I want to evaluate the partition function is I of course want to go towards the free energy, and I evaluate this partition function in the equilibrium setting where the temperature is 1 by beta, and this beta may contain many dimensionless coupling constants. If you take the simple Ising model without any magnetic field, there is a single coupling constant which will be, it will be the temperature divided by the exchange constant or something like this. And we would like to be in the non-perturbative regime of some of these parameters. So if I want to know what is the probability of realization, statistical weight associated with a configuration C, that's of course given by the Gibbs weight. And the free energy, once I compute this partition function, is simply minus T times log Z. So this is a very, very straightforward, very elementary thing by now. So the problem of course is that we cannot evaluate this, we cannot go through this process because we don't, it's too difficult a problem to address. So the problem statement, the problem we are going to, the way we are going to pose this problem of getting some non-perturbative result is, rather than trying to get an exact expression for this in some expansion or something like this to some order or in the parameter or something, what we would like to do is we would like to get an approximate expression for the free energy. And I am using the word approximate in a sense that it may be like a bound on the free energy, or we can say that the free energy that we are having will be of the true free energy of the system will be always less than some free energy that we are going to compute or something like that. It is in that sense that I mean approximate. Okay. So of course, once you have the free energy, you can compute variety of things. In case you want some observable, you can also evaluate it directly once you know this this density matrix or this Gibbs probability distribution. So this is the well-known problem. So what are we going to do? So I mentioned that there are two approaches. One is that you could just use some variational ideas, and the other I mentioned that you can just look at the Hamiltonian and try to make some approximations directly in the Hamiltonian. So today what I am going to discuss is I am going to discuss the variational approaches to the problem, and the idea here is to come up with a different Hamiltonian. So let me explain what is the idea here. So we have a problem, we have a set of configurations, and there is an energy associated with each configuration, and there is a Hamiltonian that determines the probability of the configuration. Now we are not able to solve this problem with the given Hamiltonian, the one that is of interest to us, say for example the Ising model. So the idea of Feynman variational principle is to find another Hamiltonian which we call as H lambda. And what is this lambda here? The lambda is a set of parameters as I will describe momentarily. The important point is this H lambda will give me an energy over the same set of configurations. So in some sense the degrees of freedom and the arena, all of those are the same. What is different is I am choosing some kind of trial Hamiltonian. This is some kind of Hamiltonian which I am going to pretend is the proxy for my real Hamiltonian. Okay. So now what is this lambda? I said that this lambda is a set of parameters that we use to describe this Hamiltonian itself. Mind you that they are not same, they may be related, but they are not same as the coupling constants of my original Hamiltonian, the one that I really want to solve. So these could be some other parameters in principle. Okay. So there could be more than one. So we will just collectively call them lambda. Okay. So this is what we are going to do. So suppose you give me such Hamiltonian, you can compute the partition function associated with that Hamiltonian. So we'll call it Z lambda, and there is a probability distribution we can define associated with this Hamiltonian, which is just the Gibbs probability distribution the standard equilibrium probability distribution, and we are keeping this system with this H lambda at the same temperature as the system that we originally wanted to study. Okay, and there is a free energy associated with this Hamiltonian H lambda. Okay, so that is what we call F lambda. Okay, and just to complete the story, if I want to compute any observable, I will simply use this rho lambda and then compute the value of the observable by using the probability distribution given by rho lambda. All straightforward, except that you may wonder, what do I mean by H lambda and what am I going to do with it? Okay, all right. So now what I am going to say is I am going to use this proxy Hamiltonian H lambda to estimate or bound or approximate the free energy of our system. That is what I am claiming. So how do we do this? Okay, please follow me carefully. So I am going to find the partition function of my original system. So this is sum over the configuration e to the minus beta hc, h is my original Hamiltonian. Now everything here is real numbers and so on, and this is e to the minus beta, there is no operator and so on, everything is, this is the energy associated with configuration. So what I can do is I can sum over c, and I take e to the minus beta h lambda of c, there is of c here, this h lambda is the energy associated with the configuration c, and then I am just multiplying and dividing by e to the minus h lambda c basically, that is what I am doing here. But now you see that this term here can be interpreted as z lambda, the partition function has to lambda Hamiltonian, times the expectation value of this object, right. So the expectation value is the rho lambda here, and that is why I get z lambda. If I put rho lambda of c, I am summing over all configurations, so I will get the expectation value of this, on which ensemble, on the ensemble corresponding to the lambda system. So that is why there is a subscript lambda here. So I have mentioned here, you should carefully understand what I mean by all this. Yeah, there's the small typo here which will correct in the notes. So this h lambda of c. Okay. So now all I do is take the I find the expression of free energy. So that will be minus t log z. So that will be just f, which we have defined already. And when I do minus t log z lambda, I will get f lambda, and then I will get minus t log of this quantity, which I have formally written down here as expectation value of e to the minus beta h minus h lambda evaluated on the lambda ensemble. Now at this stage this is an exact result, but being exact is not very helpful, because it could be as difficult to evaluate this object as anything else here. Like for example, it could be as difficult to evaluate as this partition function. So this looks like we are running into a dead end here. Not quite, because what we are going to do is we are going to try to find a way to find a bound on this guy, on this term. Can we use some mathematical tricks or some theorems of mathematics to try and put some bound on this? So this is what we are going to do. So to do this, I have to bring in a mathematical result which is called as Jensen's inequality. So this is a result on a class of functions called as convex functions. So what is a convex function? So let's take a very simple example. Think of a function defined for any real variable. So I have some function f of x. So this is a real variable and it is convex if the value of the function at some intermediate point between 2 points. So this is also called the convex linear combination of 2 points. So if I start with x1 and x2 and p is some number between 0 and 1, so it's some number like 0.2 or something like this, then this quantity, this point here is the linear combination, the convex linear combination. It's a point lying between, if you wish, x1 and x2. Okay. What this inequality says is that, what the definition of the function says is that the value of the function evaluated at the midpoint is less than or equal to the convex linear combination of the values of the function here and here. So the idea is, if you make a linear extrapolation on this between these 2 points of this function, knowing the value here and here, that linear extrapolation function, which is denoted by this line, will always be greater than the actual value of the function. So roughly it's function that is somewhat like, it's like a convex mirror or something like that. That is what we mean by convex. Okay, so this is a convex function. So what can we do with convex functions? So first thing is, if a function is convex, you can actually generalize its definition of this property of convexity to something more. So suppose I take n points, right? I take n points xi, I can be any number of points, and I find numbers pi which are all between 0 and 1 in such a way that they add up to 1. Then you can see that this term, which is function which is the weighted average of these coordinates xi, the function evaluated at that will be less than or equal to the weighted average of the values of the function at those points. Okay, so this simple generalization of that, you can see that just by iterating over this, you can just by inductively you can prove this. Okay, so this is always true for a convex function. Okay, so what is an example of a convex function? If you think of the function e to the minus x, which is the function that we'll need, that's why I'm giving that as an example, that is a convex function. And of course, you should maybe pause the video and write down a couple of convex functions so that you that are not e to the minus x, so that you make sure that you have some conceptual understanding of what convex functions are. Okay, so what can we do with convex functions? To understand how we are going to apply it to our problem, note that if I have n points xi, I can think of these weights pi such that they add up to 1, and every pi is between 0 and 1, and the sum over all the weights is equal to 1. I can interpret pi as if they are probabilities. Okay, all right. So noting that this object has interpretation of probability, we can now similarly think of sum over configurations of rho lambda c equal to 1. So this is like our pi. What we can now do is we can evaluate the exponential of any observable. So let O be an observable. So what I'm going to do is I'm going to find out the average value of e to the minus O evaluated in that configuration. But e to the minus x, as we saw, is a convex function. Therefore, this must be greater than or equal to the function evaluated at the average value of this O, correct? So that must be greater than or, that's what this thing is saying, right? So this must be greater than or equal to e to the minus sum over configurations rho lambda OC, like this. So this implies that the expectation value of e to the minus O evaluated in the lambda ensemble is greater than or equal to exponential of the average value of O evaluated on lambda. That's what it says. Okay. So I have done this for the exponential. Actually, this is true for any convex function. E to the minus x is convex. So this is certainly true for that. but it's also true for any other convex function, and this goes by the name of Jensen's inequality. So we have used Jensen's inequality to arrive at a result which says that e to the minus O lambda is greater than or equal to e to the minus expectation value of O evaluated in the lambda ensemble. So how can we use that? All right. So I start with this expression of the free energy, which is an exact expression. Now I observe that this involves expectation value of minus beta h minus h lambda evaluated in the lambda ensemble. Now I use Jensen's inequality, which says this quantity is greater than or equal to e to the minus beta expectation value of h minus h lambda evaluated in the lambda ensemble, which means the log of this is greater than or equal to the log of that, which means when I take minus t times that, this quantity I have to replace, I have to make this into a less than because of this minus sign. And now when I take log of e to the minus beta h minus h lambda, this is just a number, e to the minus beta some number, that beta and t will cancel and the minus and minus will cancel, and I get this very nice result that the free energy of my system is less than or equal to the free energy of the pure lambda system and this quantity evaluated in the lambda ensemble. Okay. So this is the Feynman variational principle. So Feynman says that the free energy can be bounded by any Hamiltonian with a parameter lambda, right? Parameters it could be, which is like this. Okay. So that's the bound on the free energy. Okay, very good. So what can I do with this? Okay. So now what I realize is that the true free energy of my system is bounded above. So that's why it's upper bound. So this is this f lambda u, which is the sum of f lambda and the expectation value of h minus h lambda evaluated in that ensemble lambda. This is an upper bound of my free energy, my actual free energy. So what should I do to find the best possible bound? I should try to find the parameters lambda such that fu of lambda is minimized. That choice of lambda will ensure that the bound that I have for free energy is the closest bound within this way of parameterizing the Hamiltonian using h lambda. Okay. So in general, as I pointed out, lambda could be many parameters. We are just schematically writing it as just one lambda as a symbol. And the way we will find the minimum value or the optimal value of lambda is by finding the minimum of fu, and that certainly has a necessary condition, may not be sufficient but definitely necessary, that the derivative of this fu, the upper bound which is a function of lambda, is the derivative of that with respect to lambda vanishes there. So that definitely at least ensures that we are at some extremum point of such a trial free energy. So now you see the variational principle. So you are saying that you are going to construct some h lambda, some other Hamiltonian with some parameter lambda, and you are going to vary the parameters of that Hamiltonian to make the free energy of this system defined in this fashion, f lambda plus h minus h lambda, that is the bound of the free energy of our system. And note that this h has all the coupling constants that we want, right? And for every set of coupling constants that are in h, you may have a different lambda minimum. And what we have to do is we have to compute, if you change the coupling constants of h, you have to recompute the lambda minimum and then use the h lambda m to compute any observable, right? So the h lambda will be the proxy. It will behave as if we believe that our system is now similar to what is described by h lambda. Okay, and the most important thing here is that this exercise of computing the lambda m for a given set of coupling constant will be carried forth in a non-perturbative fashion. We will not assume that any coupling constant is small or something like this. So, we may have to take recourse of numerical methods, oftentimes that is true, and we have to yet solve the problem without making any perturbative approximation on the coupling constants of our original problem. Okay. All right. So, now this is all very nice in general, but suppose I give you a problem, how do you choose what is H lambda? How do you find the Hamiltonian, some parameterized by something called lambda, that will capture this physics for us, that will capture the physics of the system that we want to study. Okay. All right. So, this is a good time to summarize this lecture. So, the main things that we studied in this lecture are, if you want to study physics in some interesting regime, like for example near a phase transitions, etc., then the coupling constants of the theory that we started off with, typically some microscopic theory like the Ising model or something like that, they will turn out to be in the non-perturbative regime. So, you have to come up with some way of studying them in a non-perturbative fashion. So, in this lecture, we visited the idea of the Feynman variational principle. So, the idea there is to replace or find a proxy Hamiltonian for our system and let that proxy Hamiltonian have a set of parameters, use the proxy Hamiltonian to find a bound on the free energy of our Hamiltonian, and then we find the parameters of the proxy Hamiltonian such that that bound is the tightest, and those parameters will describe the proxy system for us, and then we can go ahead with the computations of that. Okay. So, this is the idea of the Feynman variational principle, and what we will do in the next lecture is that we will use the Feynman variational principle to solve the Ising model on a d-dimensional cubic lattice, and the d can be any dimension. I am sure you will enjoy that lecture coming up. So, I look forward to seeing you there. Thank you.